Cyclic forms of monosaccharides. This is an example of a cyclic form of D-glucose. This type of monosaccharide contains 6 carbon atoms. The type of ring that will enable to accommodate this sugar is the pyranose ring. Cyclic structure. Aldehydes and ketones react with alcohol to form hemiacetals. Cyclic hemiacetals form readily when hydroxyl and carbonyl groups are part of the same molecule, and their interaction can form a 5 or a 6-membered ring. For a 5-membered ring, the type of ring that will be formed is furanose ring. For a 6-membered ring, the type of ring that will be formed is pyranose ring. Special terminology for cyclic monosaccharide structures. Anomers. These are the hemiacetal carbon atom that are present in a cyclic monosaccharide structure. It is the carbon atom that is bonded to an hydroxyl group and to the oxygen atom in the heterocyclic ring. Cyclic monosaccharide formation always produces 2 stereoisomers. These are the alpha and the beta form. Anomers are cyclic monosaccharides that differ only in the position of the substituents on the anomeric carbon atom. This is an example of an alpha and a beta anomer. On the first picture, we will see the open structure. This is also called the Fischer projection structure. On the next picture, we will see the closed structure, which is also called the Haworth projection formula. The ones that are being encircled are the hydroxyl group that are found on the carbon 1 atom of the ring pyranose. For alpha glucose, we will see that the hydroxyl group will be attached on the C1 carbon, specifically below. Whereas for the beta, we will see on the C1 part of the ring, it is positioned in the upper portion. This is an example of an alpha and beta anomers. The ones being highlighted are the hydroxyl groups. For the alpha glucose, hydroxyl group is being placed below. For the beta group, the hydroxyl group will be placed on top. This will be on the C1 of the pyranose ring. Cyclic forms of other monosaccharide. A cyclic monosaccharide containing 6-atom ring is called pyranose, whereas a 5-atom ring is called furanose. The Haworth projection formula. This is a 2-dimensional structural notation that specifies the 3-dimensional structure of a cyclic form of monosaccharide. The founder of the Haworth projection is Mr. Walter Norman Haworth. In a Haworth projection, the hemiacetal ring system is viewed edge-on, with the oxygen ring atom at the upper right for the 6-membered ring and at the top for the 5-membered ring. This will be the oxygen. for pyranose ring. And this will be the oxygen that is present in the furanose ring. The D and the L form of monosaccharide. The D and the L form of a monosaccharide is determined by the position of the terminal alcohol, or this is the CH2OH on the highest numbered ring carbon atom. In the D form, this group is being positioned above the ring. In the L form, the terminal CH2OH is positioned below the ring. On the first picture, it will show us the D form. It will be seen on the highest carbon and it is placed on top. On the L form, as you can see on the picture, the CH2OH will be positioned below the ring. For the D and the L form of the monosaccharide, we are going to take a look at the structure, get the highest numbered carbon atom, and then that will be the terminal alcohol or the terminal CH2OH. If it is in D form, then we are going to place it on top. If it is in L form, then we are going to place the terminal alcohol below the ring. Alpha and beta configuration. Alpha or beta configuration is determined by the position of the hydroxyl group on carbon 1. In a beta configuration, the group will be placed on top. In an alpha configuration, the group will be placed below. This is a picture that shows the location of the alpha and the beta configuration, including the D configuration. If we want to locate the alpha and beta configuration, we are going to take a look at carbon number 1. If the hydroxyl group is being placed below, then this will be alpha. If the hydroxyl group is being placed on top, then this will be beta. On the picture, we can also see the highest carbon atom that bears our terminal alcohol. They are both placed on top, therefore, they are also in D configuration. The name of the first monosaccharide is alpha-D-glucose, whereas on the second, it will be beta-D-glucose. A wavy line. In situations where alpha or beta configurations does not matter, the hydroxyl group in carbon number 1 is placed in a horizontal position and a wavy line is being used as the bond that will connect it to the ring. Based on the given picture, we will see a wavy line. This wavy line would mean that the alpha or the beta configuration does not matter. Identity of each monosaccharides. The specific identity of a monosaccharide is determined by the positioning of the other hydroxyl group in the Haworth projection formula. Bear in mind that any hydroxyl groups at the chiral center that is to the right in a Fisher projection points down in Haworth projection formula. On the other hand, any group to the left in a Fisher projection formula points up in Haworth projection formula. Let us now talk about the Haworth projection formula. These are the rings that are being used in the Haworth projection formula. For 6 carbon atoms, we make use of the pyranose ring. These are commonly used by the aldose or aldehyde group that are sugar. We count the number of carbon atoms: carbon number 1, carbon number 2, 3, 4, 5, and 6. Next, for 5 carbon atoms, we make use of a furanose ring. These are for the aldose and the ketose group. You are going to count the number of carbon atoms, starting with carbon number 1, 2, 3, 4, and 5. The ones that are located here and here are oxygen bonds. How were the bonds being formed in a pyran ring? Let us talk about the carbon with a double bond alcohol and a hydrogen. When a hydrogen is being added to this group, to the aldehyde group, if you are going to add hydrogen, oxygen is more electronegative than hydrogen. So what happens? The carbon will now bond with oxygen, and oxygen will also bond with hydrogen. So, if you're able to observe, the double bond was no longer there because hydrogen was able to bond with oxygen. And so, this oxygen has already given up its double bond in order to have a covalent bonding with hydrogen. If we are going to look at the structure, this is now COH. So let us now take a look at the D-glucose structure. So we have C, double bond O, and hydrogen. We have here the terminal alcohol. And then we have carbons number 2, 3, 4, and 5. We have to take into consideration that the carbon that has the highest chiral center, C5, it is now going to move in a counterclockwise manner together with the hydroxyl group. What happens now is that the hydrogen will bond with oxygen. As a result, it is going to form COH. Next, what happens with our carbon and oxygen? They are now going to form a ring. So, let us write again the structure. This is now our carbon number 5. This will be our oxygen, and our oxygen was able to bond with carbon number 1. So, based on what we have discussed a while ago, our carbon now, carbon number 1 is bonded with oxygen and hydrogen. And then, do not forget that our carbon still has a hydrogen in it. This is the hydrogen. So, we are going to put hydrogen here, and it means to say there is still a hydrogen here. Okay? So, this is the bond formation. Again, if we are going to try to locate where is the COH of our carbon number 5. Here is your carbon number 5. C, here is the oxygen. Where is the hydrogen? This is the hydrogen. What about for carbon number 1? This is carbon number 1. This is the double bond O, and this is the hydrogen. So, that is basically how the ring was formed. So, we have carbon number 1, carbon number 2, 3, 4, carbon number 5. Okay? So, this is your carbon number 5. Go back to our Fisher projection. You will see on the Fisher projection, after carbon number 5, there is an alcohol. And this is your CH2OH. So, therefore, we are going to place it number 6 because of the terminal alcohol. This is the formation of the ring for the pyranose. We are now going to discuss the ring formation, which involves 5 carbon atoms, and it is a haldehyde group. Oxygen, that is highly electronegative, will bond with hydrogen, forming carbon, oxygen, and hydrogen. The double bond will now become a single bond because our oxygen bonded with hydrogen. As a result, COH will be formed. And of course, we have here the hydrogen bond. Then, we are going to try the D-ribose. D-ribose is an example of a sugar that contains 5 carbon atoms. So, on top, we have the aldehyde group. At the bottom, we have the alcohol. There are a total of 5 carbon atoms. So, we have 2. So, 1, 2, 3, 4, and 5. So, we are going to count the number of carbon atoms. We have carbon number 1, 2, 3, 4, and carbon number 5. Based on our configuration, we have the D-ribose. In the D-ribose, we are going to get the highest chiral center, and this is our carbon number 4. The highest chiral center, and then the configuration, which is D. This will now form a ring with our carbon number 5. So, our carbon number 4 will form a ring to our carbon number 1. So, this is now what happens. For our carbon number 1, again, as what we have stated a while ago, carbon, the double bond will now become a single bond, forming COH. And then we also have the hydrogen group. This is now our carbon number 1. Now, what happened is that there is a ring formation. So, we have here oxygen and our carbon number 4. Okay, so if you are going to determine carbon number 4 has hydroxyl group attached to it. It was the one that went in a counterclockwise manner. It bonded with our functional group, carbon number 1. So this is for carbon number 4, carbon, this is the oxygen. And then, where is the hydrogen? This is the hydrogen. So we have carbon number 4, C, O, and H. Next, what happened to our carbon number 1? Carbon number 1, the double bond was no longer present since it bonded with the hydrogen, and it also has an additional hydrogen group there. Okay, so this was the illustration that we did a while ago. Next, we are going to continue. So we have here the structure. So we have carbon number 1, carbon number 2, carbon number 3. This is now our carbon number 4. Next, if we are going to observe the structure, after carbon number 4, we have here attached is your carbon number 5. So this is here where we have carbon number 5. This is now the formation of the ring in an aldehyde group, particularly an aldose that contains 5 carbon atoms. What about if we have a ketone? For a ketone, we have here the C double bond O. Upon the addition of hydrogen, what happened? Since oxygen is highly electronegative, it will still bond with our hydrogen, forming carbon, single bond, oxygen, single bond, hydrogen. So as we have observed, the double bond is no longer present because our oxygen bonded with hydrogen. As a result, we have here COH. Let us try to determine the D-fructose. How is the ring being formed in a ketone? So, we always start with our functional group that is present on the second carbon. Then, we have here an alcohol and another alcohol that is found on the terminal ends. Then, fructose contains 6 carbon atoms. A ketone that contains 6 carbon atom that is found at the center. So we have here, okay, so we are going to count the number of carbon. 1, 2, 3, 4, 5, and 6. After we were able to write the 2 terminal ends and the functional group that is found on the second carbon, we are now going to determine the configuration. So for our D-fructose, we are going to get the highest chiral center, and this is our C5. So this would now mean in a D configuration that the hydroxyl group is found on the right. So again, after we were able to find the highest chiral center, this is now going to form a ring with our functional group. So C5 will now go to C2 to form a ring. Okay, so how is the ring being formed? We have here C2. Okay, this is our carbon number 2, the one that is ketone. So what happened? Okay, upon the addition of our hydrogen, so carbon number 5 bonded with our ketone, so the oxygen bonded with the hydrogen that is present in our carbon number 5. Next, we have here a ring formation, and this is now our carbon number 5. So carbon number 5, this one is C. This is the oxygen, and where is the hydrogen? Okay, it is here. It bonded. It formed the ring. It bonded with carbon number 2. What happened to the double bond of our oxygen in carbon number 2? Since it is a ketone, it is no longer present. And what happened? It bonded with hydrogen. Okay, so for carbon number 5, we have here hydroxyl group. So this is carbon, oxygen, and hydrogen. For carbon number 2, we have here the double bond is no longer present. So double bond O, which is no longer present because it bonded with hydrogen. Okay, now we are going to continue the ring. So this is C2, this now is C3, C4. Okay, so let us take a look at C5. C5 now, in a Fisher projection formula, our C5 has still C6. Okay, so it is in C6. Okay, so this is where C6 is present. Okay, C6. Okay, so attached to our C5 is C6. So, what about in the C2? Okay, C2, as we can see here, C2, attached here is our C1. Okay, so in the C2, we have here attached is the C1. Okay, so let us try to substitute our C6 and C1. Okay, so for our C6, we have CH2OH. So therefore, what about for our C1? C1 is still CH2OH. Okay, so in a ketone furanose ring, we have two alcohols that are being attached. The one, okay, the first alcohol is attached to carbon number 2 and then together with the hydroxyl group. Next, in carbon number 5, we also have attached here is your carbon number 6, which is an alcohol. This is now the furanose ring that involves 6 carbon atoms and a ketone. So it means to say this is a ketone body that contains sugar. Haworth projection form is determined by the terminal CH2OH group on the highest carbon ring. So again, in the Haworth projection, we are going to determine the D and L form. Just like what we did in the open chain, in the Fisher projection, we are also going to do the same in the Haworth projection or in the closed chain. We are going to take into consideration the D and the L form. If we are going to take into consideration the D and the L form, we are going to locate the terminal CH2OH. This is the one that has the highest carbon ring atom. So, for our D or L form, in a Haworth projection, we are always going to locate it on this side. The one that has the highest. So, if we are going to locate our D or L form, we always take a look at these sides. They are on the side that has the highest carbon ring atom. Now, after we were able to locate the one with the highest ring form, then it is now time for us to determine how is the D and how is the L being formed. So, for the D form, we always put the CH2OH on top. Again, for the D form, we always put the CH2OH on top. For the L form, we always put the CH2OH below. Okay? So, up, down. Okay? So, in here, it is in D form. Therefore, we are going to place it up. Okay? We are going to place our CH2OH on top. If it is in L form, we are going to place the CH2OH down, below. Same as true in a furanose. If it is in D form, then we are going to place the CH2OH on top. In the L form, we will be placing the CH2OH or the terminal alcohol down. So once again, in the Haworth projection, our basis will be the highest carbon atom in a ring. So we have here the terminal carbon and this is your CH2OH. If it is in D form, then it means to say you are going to place it on top. If it is an L form, then it means to say you are going to place it down or below. Same is true with the furanose. If it is in D form, you are going to place it on top. And if it is in L form, you are going to place it below. In Haworth projection, the alpha and beta configuration is also determined by a hydroxyl group that is located in carbon number 1. Alpha means below, beta means above. These are the two rings that are being used in our Haworth projection. Alpha, I used to memorize it in our own dialect. Ilalim, lalam, lalim. So, this is located below. Beta, on the other hand, for me, it looks like it is letter B. And so, babaw, ibabaw, above. That is how I memorize the alpha and the beta configuration. L for low, lalim, below. For me, this beta looks like it is letter B. So it is ibabaw, above, babaw. Let us now put the different alpha or beta configuration in our pyran ring and furan ring. Or, since they are sugar, they are now pyranose ring and furanose ring. We have here alpha. Again, when we talk about alpha, it is pointing downwards. So, our main focus will be on carbon number 1. For alpha, we are now going to position them and we will be placing our hydroxyl group below. For beta, again, our basis will be on carbon number 1. We will be moving our hydroxyl group on top. Next, for our pyranose ring, we are going to move, since it is alpha, we are going to move it below. For our beta, we are going to place our hydroxyl group on top. Again, in Haworth projection, we are going to determine if it is alpha or beta in the C1 location in the pyranose ring or in the furanose ring. Now, if it is alpha, it means to say we are going to place it in the downward, or our hydroxyl group will be placed below. If it is beta, we are still going to get the hydroxyl group and place it in the upper portion. This is now beta. Next, in a furanose ring, we are going to place our hydroxyl group below because this one is alpha. Next, in our furanose ring that states it is in beta configuration, then we will be putting our hydroxyl group in an upward manner or above. Our main location will be on the C1 of the rings. In Haworth projection, any hydroxyl group that is to the right in Fisher projection formula points down in Haworth projection. Again, any hydroxyl group that is to the right in a Fisher projection formula will point down in Haworth projection. So, what we did in the Fisher, if you still remember, we divided the lines into two. So, there will be a left side and there will be a right side. So, let us going to do this again. Left side, right side. Any substituents, hydroxyl group, hydrogen group that are placed on the right side of the Fisher projection formula, we are going to place them downwards. in a Haworth projection. Again, in Haworth projection, any hydroxyl group or hydrogen or any substituents that are located on the right side in a Fisher projection formula, we are going to point them downwards. So, we have here an example, OH, H, OH. So, I'm going to place them downwards. OH, then hydrogen, next hydroxyl. This is just an example. We are not pertaining to any groups. We are just portraying that any hydroxyl group or any group that is placed on the right side of the Fisher projection formula, then we are going to put them downwards. This is now your Haworth projection wherein the Fisher formulas are on the right side. And in Haworth projection, what happened is that we place them downwards. Any hydroxyl group that is to the left in a Fisher projection formula will be pointing upwards in Haworth projection. So again, I am not pertaining to any groups, any monosaccharide. I am just referring to how we are going to place them in Haworth projection. So again, the Fisher projection, we divide it into two so that we will have a left side and a right side. So, for example, we have here hydrogen, hydroxyl, and hydrogen. So, hydrogen, hydroxyl, and hydrogen. Hydrogen, hydroxyl, and hydrogen. I mean hydrogen. So, this one is hydrogen. So, these are all located on top. Again, in Haworth projection, any groups, hydroxyl group, hydrogen group, any substituents that are located on the left side of the Fisher projection formula, they are to be placed on top in Haworth projection. So we have here hydrogen, hydroxide, hydrogen. Okay? So, we are now going to start our conversion from Fisher projection to Haworth projection. You listen carefully so that we will be finishing on time. So, we are again going to draw the Fisher projection. Okay? So, I'm going to draw a line. And then, I'm going to write the functional group. Since this is a D-glucose, again, so after we were able to write the functional group, then we will write the terminal end. This is an alcohol. Then we are going to count the number of carbon. Glucose has 6 carbon, therefore we have 1, 2, 3, 4, 5, and 6. Okay, so in counting, of course, we know that this will be our carbon number 1, carbon number 2, 3, 4, 5, and carbon number 6. Now, we take into consideration the highest chiral center. Okay, so this will be carbon number 5. Okay, carbon number 5 will be the highest chiral center. It states that it is in D-glucose, therefore we are going to put the hydroxyl group on the right side. So that we will, it will be easy for us to memorize. We may also put here left side and right side. Okay, so after we were able to determine the highest chiral center, because this one now is on the right side, that's why it is a D configuration. Okay, the next thing that we are going to do is we are now going to complete the hydrogen and hydroxyl group. So for glucose, we have right, left, right. Okay, And then we are going to complete the hydrogen structures. Okay, so we are going to double check if all of our structures are complete. So starting from carbon number 1, this is the aldehyde group, and then 2, 3, 4, 5, and 6. Okay, so this is now correct. Next, we should bear in mind that our carbon number 5, as what I have mentioned previously, forms a pyranose ring. So our carbon number 5 forms pyranose ring with our carbon number 1. And because of this, our pyranose ring was formed. Now, how are we going to start our Haworth projection? This is how I answer whenever it is pertaining to Haworth projection. Carbon number 5 and carbon number 1 will be the last. It will be my last to answer. So it means to say, I will leave this side, carbon number 1, and I will leave this side, carbon number 5 and 6. Okay? I will leave carbon number 1 and I will leave carbon number 5 and 6 in here. So, it means to say, I'm going to start with the chiral centers that are not included in the ring formation. Okay? So, again, in making the Haworth projection, I am not going to start with carbon number 1. I'm not also going to start with carbon number 6. Instead, I will be starting with carbon number 2, 3, and carbon number 4. Okay? So, I'm now going to answer this encircled one, carbon number 1, and carbon number 5 and 6 will be the last to be answered. Okay? So, let us now answer and do the Fisher projection. So, this will be carbon number 2, 3, and 4. Carbon number 2, it is located on the right side. Therefore, our hydroxyl group is to be placed below. So, our hydroxyl group is placed below. Next, our carbon number 3 is located on the left side. That is why I'm going to put the hydroxyl group on top. Next, carbon number 4, the hydroxyl group is located on the right side. Therefore, I'm going to place it below. Let us also not forget to count the rings so that we have a guide. Okay? So again, let us double check our answer. For carbon number 2, we have on the right side. That's why it is located below. Next, carbon number 3. Carbon number 3, the hydroxyl group is located on the left side. That's why it is on top. Carbon number 4, the hydroxyl group is located on the right side. That's why it is located below. Next, for our carbon number 5, this one is carbon number 5. So it has already bonded with oxygen. So what happens now is, if you still remember, where are we going to put our CH2OH if it is in D notation? Okay, so our basis here will be the CH2OH. Remember, if our notation is in D configuration, we are going to put it on top. Okay, so that is how we answer the last terminal alcohol. Okay, so our basis will be, if it is in D configuration, we will put the CH2OH on top. Next, the second circle will be the first carbon atom. Our basis, if it is alpha or beta. Okay, so on the first carbon atom, it states that beta. So it means to say, we are going to put the hydroxyl group on top. So, we will place the hydroxyl group on top. Next, let us double check if all of our hydroxyl group are present in every carbon. So, we have for carbon number 1, carbon number 2, 3, 4. Carbon number 5, the only thing that we move here is the CH2OH, and we follow the D configuration. Okay, they are complete. Now, let's complete the pair. We just put hydrogen on the opposite sides. So, this is now our beta-D glucose. Let us now do the same for our alpha-D glucose. Okay? So, once again, let us not yet answer. We won't answer the first carbon and the last carbon. So that they will be the last one. Okay? We are now going to count. So this will be our carbon number 1, carbon number 2, 3, 4, 5. Then, we are now going to put our hydroxyl group. So for our hydroxyl group on the second one, the hydroxyl is located on the right side, therefore below. Next, on the third one, hydroxyl is located on the left side, we put on top. Next, carbon number 4, hydroxyl located on the right side, we put below. Next, we now proceed with the circles, the ones that we did not answer. Okay? So, for the last carbon atom, we are going to determine if it is in D notation. Then, we are going to place the CH2OH on top. This is in D notation, so we will put it on top. Next, the second one, if it is in alpha or in beta. So, this one is in alpha. It means to say we are going to put the hydroxyl group below. Let us check if all of our hydroxyl group are present in every carbon. Yes, they are complete. So now, we will be completing their pairs. Okay, add the glucose in Haworth projection, and this will be our alpha D glucose using Haworth projection. We are now going to have another example from Fisher to Haworth projection. So, we have here the D-galactose. D-galactose is a sugar that contains 6 carbon atoms. We have carbon number 1, 2, 3, 4, 5, and 6. So, what we have written first is the functional group, and this is on the top part. Then, on the terminal end, we have your alcohol. Afterwards, we determined the configuration, and in this case, we have the D configuration. So, we are going to locate the highest chiral center, and the highest chiral center is carbon number 5. It states that it is in D configuration, therefore, we are going to put it on the right side. Afterwards, we are going to continue with the number of carbon atoms that is located at the chiral center. So we have here carbon number 2, wherein the hydroxyl group is located on the right. Then carbon number 3 and number 4, the hydroxyl group is located on the left. Then we have to bear in mind that the highest chiral center, which is our carbon number 5, is going to go to our functional group. So it will form a ring. Then, we are now ready to make the Haworth projection. So, let us also bear in mind that the last that we are going to answer will be carbon number 1 and carbon number 5, where it contains our carbon number 6. So, we are going to wait and answer this one, the last. So, this one that formed the ring will be answered later. We are going to start with carbon number 2. So in here, our hydroxyl group is located on the right side. Therefore, we are going to put it below. Next, number 3, our hydroxyl group is located on the left side. It means to say we are going to place it on top. Next, carbon number 4, it is still placed on the left side, therefore we are going to place it on top. So, we are now going to continue our placement of the hydroxyl group for the ones that we saved the last. So we have here beta. So beta D galactose. If we talk about beta D galactose, we are going to focus on the D galactose. So D, we are going to look at the last part. So the last part, we have here the CH2OH. If it is in D configuration, we are going to put it on top. Then, D, CH2OH, terminal end. Next, we have the beta. For the beta, we go to the carbon number 1. So, beta, babaw, the hydroxyl group is placed on top. Next, after that, so we were able to complete all of the hydroxyl group on the ring. Then, we are now ready to complete the hydrogen pair. So, this is now the Haworth projection for our beta D galactose. Next, let us answer the alpha D galactose. So, for our alpha D galactose, this will be the last one that I will answer. So, I will start with carbon number 2. It is on the right side, therefore, I'm going to place it below. Then, carbon number 3 and carbon number 4, it is placed on the left side, therefore, I'm going to put it on top. Next, I am now going to proceed with the configuration. So, for D configuration, I'm going to look at the last carbon ring, the one with the highest chiral center. So, D configuration, it means to say that I'm going to put the CH2OH on top. Next, alpha, it means to say I'm going to put it below, lalim. So, hydroxyl group is to be placed below. So, after being able to complete all of the hydroxyl group on their places, including the terminal alcohol, we are now going to place their pair, the hydrogen. So, this is now our alpha D galactose. Next, we are going to answer what if it is in L configuration. Same, I will be answering this later. So, for our hydroxyl group that is on the second carbon, it is on the right side. Therefore, I'm going to place it below. And then, 3 and number 4, I'm going to place it on top. Then, afterwards, I'm going to determine the place of our terminal CH2OH. This time, it is in L configuration. So, on the highest chiral ring, highest chiral center, this one now, I'm going to place the CH2OH below since it is in L configuration. Next, beta, babaw. So, I'm going to place the beta, the hydroxyl group, babaw on top. Afterwards, we are now going to complete our hydrogen bonds. This is now the Fisher to Haworth projection for our beta, alpha, D, and L galactose. So for beta, the hydroxyl group is to be placed on top on carbon number 1. For alpha, the hydroxyl group is to be placed below for carbon number 1. For D configuration, the terminal alcohol is to be placed on top. D configuration, for D configuration, the terminal alcohol is to be placed on top. Whereas for our L configuration, the terminal alcohol is to be placed below. Next, we have the Fisher to Haworth projection for our D-ribose. So, D-ribose is a sugar that contains 5 carbon atoms. We started counting the number of carbons. So, we have 1, 2, 3, 4, and 5. So, we write the functional group first that is found on top and then the terminal alcohol. Then, we complete our hydroxyl group. So, the first thing that we are going to do is to determine the configuration. So in this case, it is in D configuration. So it means to say that the highest chiral center is in the right side. So we have here the left side and the right side. So the highest chiral center is now on the right side since it is in D configuration. Then we complete all of the hydroxyl group. So in our D ribose, the hydroxyl group are placed on the right side. Then we write the ones that form the arrow. So in this case, the highest chiral center is carbon number 4. So it was the one that formed a ring in our furanose ring. Okay, so it formed a ring with our functional group. So we are now going to count our carbon. So in a furanose ring, we have carbon number 1, 2, 3, 4, and on top will be carbon number 5. So let us now answer the beta D ribose. Just like what we did before, the last one that we will answer are the carbon number 1 and the one that contains the highest chiral center. So we are going to answer this later. Okay, so we will now start with carbon number 2 and carbon number 3. So for our carbon number 2 and carbon number 3, our hydroxyl group are located on the right side. Therefore, we are going to place them below. So, the hydroxyl group for carbon number 2, hydroxyl group for carbon number 3. Next, we are now going to proceed with the circled ones. So, it is in D configuration. It means to say, if it is in D configuration, our terminal CH2OH will be on top. Next, it is in beta configuration. It means to say our hydroxyl group is placed on top. Okay, so we are now going to complete our hydrogen bonds. So this is for hydrogen bond. And then next, we will answer the alpha D ribose. So in the alpha D ribose, as being stated, we are going to answer the last two carbon that is located on the first carbon and that on the fourth and the fifth carbon atom. Okay, same. We are going to get carbon number 2 and place the hydroxyl group below since it is located on the right side. Then, carbon number 3, we are going to put the hydroxyl group still below since they are located on the right side. Then, for the deconfiguration, we will put the alcohol on the carbon number 4 and carbon number 5. We are going to put it on top. If it is in alpha configuration, lalim, then ilalagay natin sa ilalim. Okay? L, lalim. So, alpha configuration, it looks like it is letter L. We are going to put the hydroxyl group below. Then, we are going to continue with the hydrogen pairs. So, what if it is in beta L ribose? So we are to answer this one later. So for carbon number 2, hydroxyl group is located on the right side. We will put it below. Then carbon number 3, the hydroxyl group is located on the right side also. Then we will put it below. It is in L configuration. Therefore, our CH2OH this time is being placed below. Okay? Next, beta configuration. It means to say our hydroxyl group babaw, above, on top. Then we will continue with the hydrogen pairs. So this is now the Fisher to Haworth projection for our ribose. So if it is in beta configuration, then it means to say we are going to locate carbon number 1 and put our hydroxyl group on top. If it is in alpha configuration, we are going to locate our carbon number 1 and put the hydroxyl group below.
If it is in D configuration, we are going to put the terminal alcohol that is found on the last carbon in a ring on top. On top. If it is in L configuration, we are going to put the terminal alcohol on the last carbon below. Next, we are going to answer the Fisher to Haworth projection for fructose. In fructose, it has 6 carbon atoms, and we have here a ketone that is the functional group. So, we are going to write the terminal alcohol that is found on top and at the bottom. Then, on the second carbon will be a carbonyl group. Then afterwards, we are going to locate the carbon that contains the highest chiral center, and this is our carbon number 5. Since it is in D configuration, it means to say it is on the right side. Then it will form a ring with our functional group in carbon number 2. So, afterwards, we are going to complete our structure by writing the hydroxyl group on their corresponding places. Carbon number 3, hydroxyl group is located on the left side. Carbon number 4, hydroxyl group is located on the right side. We are now going to start answering our Haworth projection for beta D fructose. So, we are going to answer this later. Okay, so we will start with carbon number 3, wherein the hydroxyl group is located on the left side. It means to say we are going to put it on top. And then carbon number 4, hydroxyl group is located on the right side. We are going to put it below. It is in D configuration. It means to say we are going to put our alcohol on top. Next, it is in beta configuration. It means to say we are going to put our hydroxyl group above. So, for a ketone, the pair of our carbon number 2 will be hydroxyl group and another alcohol. Based on our structure, the ketone, carbon number 2, is attached to carbon number 1, which is an alcohol. That's why on the carbon number 2, attached here is our hydroxyl group and carbon number 1, which is the alcohol. Then, after we're able to complete everything, we are going to write their corresponding pairs. Next, what if it is in alpha D fructose? Same, we are going to answer this later. So, carbon number 3, the hydroxyl group is located on the left side. We place it on top. Carbon number 4, hydroxyl group is located on the right side. We place it below. D configuration, it means to say our terminal alcohol is located on top. L or alpha, it means to say low, lalim. We are going to place our hydroxyl group below. Then, since this one is a ketone, the pair of our carbon number 2 is a hydroxyl group and attached to it is an alcohol. Okay. Then, we are going to continue with the remaining hydrogen. So, let's now proceed to beta L fructose. So, this will be the last one that we will answer. So, in beta L fructose, we are going to start with carbon number 3. And in here, our hydroxyl group is on the left side. Therefore, we are going to put it on top. Carbon number 4 is on the right side. We're going to put it below. L configuration, it means to say our CH2OH is located below. And in beta configuration, it means to say our hydroxyl group is found on top. And it pairs with carbon number 1, CH2OH. Then we complete the corresponding hydrogen pairs. Now for our alpha L fructose, same. We are going to answer carbon number 3 first. This is located on the left side. That's why we are going to put it on top. Carbon number 4, it is on the right side. That's why we are going to put it below. L configuration, it means to say we are going to put the CH2OH below. Alpha configuration, it means to say we are going to put the hydroxyl group below, and this will pair with our carbon number 1, which is an alcohol. Then this will be their corresponding hydrogen pairs. So in here, for our fructose, if it is in beta configuration, we have to take into consideration the carbon number 2. So in carbon number 2, it has to have a hydroxyl group that is placed on top. Then it pairs with an alcohol. This will be carbon number 1. For alpha, then we are going to again locate carbon number 2. Alpha, it means to say low, lalim, put the hydroxyl group below, and it pairs with the alcohol. For the configuration, as we can see, we have the CH2OH, the terminal group that is placed on top. Then, for our L configuration, the CH2OH is being placed below. This is the Fisher to Haworth projection for fructose.